Assalamu alaikum. The topic of presentation today is lasers. At the end of this presentation, the audience will be able to describe what is laser, explain how laser is produced, describe phenomena of resonance, describe different laser modes, enlist effects of laser energy on tissue, classify laser safety, enlist lasers used in ophthalmology and their uses, name investigational uses of lasers in ophthalmology. Laser is an acronym which stands for
light amplification with standard light amplification with standard emission of
Radi- light amplification by stimulated emission of radiation. Laser light is coherent, which means that all the waves are in phase. Monochromatic, it has a single wavelength. And collimated, that means all the rays are parallel to each other. Lasers are named according to their active medium. Active medium contains the atoms which will undergo stimulated emission. The laser active medium can be solid, liquid, or gas. Solid laser medium is present in ND-YAG laser. Liquid medium requires a dye like rhodamine or fluorescein, and gas medium is present in argon laser, krypton laser, and carbon dioxide laser. Source of energy pump can be electrical discharge, another laser which may stimulate the laser that is being used, or incoherent light which converts the laser into coherent light. Actually, lasers are very inefficient. Their actual luminous flux emitted by laser is relatively small, but it is concentrated into an exceedingly narrow and parallel bright beam, which increases the luminous intensity of the laser. So, what is luminous flux? Luminous flux is the quantity of light emitted, and luminous intensity is the light emitted per unit solid angle. Irradiance is the light per unit area incident at the surface. These three terms will be used in this slide. A laser producing 5 lumen of luminous flux will have a beam of luminous intensity 500 million candela because it is concentrated at a single point. And a 1 watt laser produces a retinal irradiance of 100 million times greater than that of a 100-watt incandescent bulb. Laser energy is produced through three stages: pumping, spontaneous emission, and stimulated emission. The lowest energy state at which atoms are most stable is the ground state. The absorption of energy elevates the atoms from the ground state towards the higher energy levels up to the upper laser energy level. This process is called pumping. This leads to inversion, in which the number of excited electrons is more than the unexcited electrons. But the excited electrons at the upper energy level are unstable and they spontaneously reach the ground state. The amount of light emitted is incoherent and scattered. This is called spontaneous emission, which is useless. But if an excited electron is stimulated by a photon, whose wavelength is the same that an excited electron would naturally emit, the resulting emission will be coherent and useful. This is called stimulated emission. The amount of laser energy emitted is actually very small, but it can be amplified by a process called resonance. The active laser medium is housed between two parallel transparent mirrors on each side to allow some light to leave the tube. Light is reflected and re-reflected and becomes stronger and stronger. This whole process is called resonance. There are three main laser modes: transverse mode, continuous wave mode, and Q switching mode. And there's another term called mode locking. In transverse mode, we look at closer cross sections of the laser, in which we realize that laser energy is not actually parallel; it is slightly divergent. So it is more intense at certain points and less intense at certain points. The point at which the laser is least divergent and most focused is called the fundamental mode. which can be described by the Gaussian curve shown here. It is important for focused lasers like YAG capsulotomy, but it is not so much important for PRT. Non-fundamental modes can be cancelled with the use of apertures inside the laser cavity. Continuous wave mode, when we compare it with pulse laser mode, it has a continuous wave. Uh, Continuous laser is produced over a particular period of time, and its peak and average power is the same. But in pulse laser, pulses of laser are produced at short intervals of time, and their average power and peak output power are not the same. Q switching is a mechanism in which a shutter is placed in front of one of the mirrors between which the oscillation of the beam normally occurs. Opening the shutter allows the oscillation to occur and produces a single pulse surge of stimulated emission with a duration of 2 to 30 nanoseconds. And closing it will uh, not allow the pulse to be transmitted. Lasers which are operating in mode locking or Q switching mode produce a brief pulse rather than a continuous wave of laser. So the beam from a continuous laser like argon laser has a constant power and it is more conveniently measured in watts. And 1 watt is equal to joule over second and power formula is energy over time. But the beam from a pulse laser, Nd:YAG laser, has a peak output power and it is more conveniently measured in joules because time is not being taken into consideration. Mode locking. Mode locking is the refinement of Q switching, which synchronizes the waves at some point. Like you can see the last phase over here. When they synchronize, constructive interference occurs, and this leads to summation of the wave into a higher power wave. But it is a pulsed wave which lasts about only 30 picoseconds. Effects of laser energy on tissue depend on factors like wavelength, duration of pulse, and type of the tissue pigment at which the laser is being incident. What is the wavelength of infrared radiation used in YAG capsulotomy? Hmm. Effects of laser can be classified into three main types: ionization, thermal effects, and photochemical effects. In ionization, the ionization mechanism is used in Nd:YAG and excimer lasers. For that, pulse duration is less than a nanosecond, and it works on the principle of molecules being converted into plasma. This plasma is a high temperature and it can lead to tissue disruption by the produced photons. Thermal effect is used in carbon dioxide laser and argon laser. Light energy is converted into heat energy, and the pulse duration is between few microseconds to 10 seconds. Over there, it was in nanoseconds. Here, it's few microseconds to 10 seconds. So we talked about pigment. Melanin absorbs most of the visible spectrum, and it is present in the retinal pigment epithelial layer and the choroid. Xanthophyll absorbs blue light. It is present in the macula, and hemoglobin absorbs blue, green, and yellow light. Uh, an increase of 10 to 20 degrees centigrade rise in temperature is beneficial because it leads to photocoagulation. But if the temperature of the tissue rises to 100 degrees centigrade, this can lead to water vaporization and this will lead to damage of the tissue. Photochemical effects use pulse duration of more than 10 seconds, and for that, shorter wavelengths like blue light or ultraviolet light is used. And argon lasers use this mechanism for retinal photocoagulation, and a filter is incorporated to protect the operator from the photochemical light. According to laser safety, lasers used in ophthalmology are categorized as class 3B or 4, which can cause significant damage or irreversible damage. So, some safety protocols have to be used. Shutters or filters are installed in the laser machines so that laser light is absorbed by them, when fired, and other wavelengths are transmitted so that the observer can see the retina that is being lased. Secondly, laser area should be free of personnel. Essential attendants should wear safety goggles. Laser used in ophthalmology can be delivered via fiber optic cable through the slit lamp, indirect ophthalmoscope. This is a slit lamp laser, this is indirect ophthalmoscope, and this is endolaser probe. These are the lasers that will be discussed. Argon blue-green laser emits a mixture of 70% 488 nanometers and 514 nanometers 30%. Newer lasers emit green light. Green light is better than blue light because blue light is absorbed by the macula and which damages the macula. So green light is used, which is absorbed by melanin and hemoglobin but not xanthophyll. It is used for photocoagulation of outer retina, which protects the retinal nerve fiber layer. And higher power beam is used in cataract because cataract causes scatter of the argon laser. Helium neon laser is not used isolatedly. Um, Low power gas laser, it is actually a gas laser with a wavelength of 632.8 nanometers, which is used as an aiming beam for lasers which are invisible. For example, diode laser and DAG laser are actually invisible. So helium neon laser is used with these lasers to make them visible. Diode laser has a wavelength of 810 nanometers. Its mode is continuous wave mode and it generates little excess heat. It is very portable. It has low scattering and good penetration. It is only absorbed by melanin, which is present in the retinal pigment epithelium and the choroid. Other uses of diode laser are it can penetrate the sclera. So if the pupil is undilated or small, it can photocoagulate the retina even then. It is also used for photocycloablation of the ciliary body in end-stage glaucoma and photocoagulation of vascular structures in neovascular membranes and tumors and endoscopic dacryocysto which is shown over here. Erbium YAG laser, it has a wavelength of 2940 nanometers and it has a low penetration. It only penetrates the tissue by 1 micrometer, less than 1 micrometer. So its thermal effects are limited to less depth of the tissue and deeper tissues are not damaged by this layer. So it is used in lens emulsification in cataract surgery, erbium YAG laser. ND-YAG laser is the most famous that we know. It emits a radiation of 1064 nanometers. The mode is continuous wave, but Q switching is used with this continuous wave mode. It is used for posterior capsulotomy, for posterior capsular opacification, and for iridectomy in narrow angle glaucoma. Which of the following is the most essential step before planning capsulotomy? Hmm. What is the laser setting that is used in laser peripheral iridectomy? Hmm. There's another type of Nd:YAG laser which is frequency doubled Nd:YAG laser. It has a wavelength of 532 nanometers and it is the photocoagulation effect is similar to argon laser. ND-YLF laser has a wavelength of 1053 nanometers and it is used in sclerostomies, vitreous membrane dissection, and intrastromal corneal ablation during refractive surgery. Holmium laser has wavelength of 2100 nanometers. It is also used to create a sclerostomy to increase aqueous humor outflow in treatment of glaucoma. Carbon dioxide laser is not used in ophthalmology. It has a wavelength of 10,600 nanometers. And it is used to create bloodless incisions in surgery. Laser which is used in the treatment of myopia. Hmm. Excimer laser has a wavelength of 193 nanometers. It derives its name from excited dimer, in which argon fluoride is broken down, dissociates into argon and fluorine, and it emits a radiation which has a voltage of 6.4, and it is capable of breaking intramolecular bonds in PRK, LASIK, and PTK. PTK is phototherapeutic keratectomy. Investigational uses of laser are based on confocal optics. In confocal optics, imaging and illumination system focus the imaging and the illumination system focus on a single small point. This system is confocal. This produces a small area of illumination and field of view is also very small. But as the field of view is very small, this leads to a higher contrast and resolution. This is applied in scanning laser scanning confocal microscopy to view different depths of the living cornea before keratoplasty. Also employed in confocal scanning, laser ophthalmoscope when we have to perform FFA and ICGA. Confocal scanning laser tomography is used for creating a topographic map of the optic nerve head to evaluate disc damage due to glaucoma. And scanning laser polarimetry is an investigation that uses the principle of birefringence, in which light is there's double refraction of light in a transparent medium. It is used to measure the RNFL thickness, and light of 780 nanometers is used. Laser microperimetry is uses a laser beam to determine the light sensitivity of small areas of the retina and to identify small scotomas. Laser interferometry uses helium neon laser, which is a gas laser, from two different sources onto the retina. Where the two waves meet, a sine grating is produced. Reducing the distance between the two light sources will reduce the spatial frequency. Spatial frequency is the space between the dark and the light lines. The greater the space, the lower the spatial frequency, and the smaller the distance, the higher the spatial frequency. It provides estimation of visual acuity when macula is obscured by cataract. Laser Doppler flowmetry is used for assessing retinal blood flow velocity. It is based on the Doppler principle, in which a light source strikes the RBCs and it is detected by a photodetector. So, a greater shift in frequency indicates a greater blood flow velocity. The higher the velocity, the greater the shift in frequency.